So before we get started, there's one thing from the out of class exercise from Monday that I wanted to go over. So this is the out of class exercise for S3. And that was actually in the second situation. Starting with, it's going to be question 9 that would be the first part of it. But it's the presidential election exit polls. Now, they made a graph here that is one of those graphs that we've discussed is not a great way of displaying data, but they did it anyway. And that's not really the point that we're going to get to today. What they did was they polled married and not married people as to who they voted for in the election. And for married people, they found that 0.43 or 43% voted for Clinton in the last election. 0.53 or 53% voted for Trump. Of the not married people, they found that 0.55 or 55% voted for Clinton, and 0.38 or only 38% voted for Trump. And these are actually relatively accurate numbers. So the conclusion that they're drawing from this is that married people were more likely to vote for Trump, and not married people as my pen goes out there, and not married people were more likely to vote for Hillary. So do you really think being married or not married was a huge factor in who people voted for? No. This is a situation where we call it, this textbook calls it a lurking variable. In the industry and statistical practice, it's often referred to as a confounding variable. There actually is a slight difference between the two. A confounding variable is a variable that just cannot be controlled. Like in a medical study, you might have somebody who has a heart attack halfway through the medical study, but you're doing medication to, I don't know, to deal with anxiety. Well, that's a variable you cannot control, other issues that come into play, or you can't control any sort of drama that's in their life that might contribute to that anxiety. So those are confounding variables. A lurking variable is a special type of confounding variable that occurs in this case. It's not really being married or unmarried that made them more likely to vote from one candidate or the other. But what is more true about people that are not married that might make them more likely to vote for Clinton instead of Trump? In other words, what variable do you think would be a bigger determining factor rather than being married or unmarried? There we go. Yeah, if I were to take a graph of people who are less than 30 and compared to people that were older than 30 and do the same type of graph, less than 30 would probably have somewhere in the 70% that voted for Clinton. Oops, and there goes my display. Okay, so let's get back to this. So for age at less than 30, I said I'm just going to put in approximate numbers. It might be closer to like 0.7 for Clinton and 0.25 for Trump. And more than 30 oops, you might have seen the total opposite, like a 0.2 for Clinton and 0.75 for Trump. So it's a huge swing. So married people versus non-married people, the non-married people do tend to be younger. And that is that lurking variable. Now, other things that kind of come into effect there, people with college degrees are less likely to be married than people without, which is kind of a weird statistics. So if you look at college degrees versus no college degrees, that might come into effect. Okay, so that's that concept of a lurking or a confounding variable and how it affects our data. So we do have to be very careful that what our data is showing is really what we were trying to study. Did you guys have any other questions on the out-of-class exercises from S3? Okay. All right, so this was the homelessness one. They're talking about homelessness and other factors like mental illness and stuff like that. Okay, like, so some of the things they found in this study, they found that homelessness had a very strong link with older age groups. In fact, the older the person was when they became homeless, the longer they tended to stay homeless. And then other things were arrest history, police record. People with police records were more likely to be homeless or to stay homeless for longer durations. Well, one thing that might link the two of them together is employment. There's a much higher rate of unemployment with people that have an arrest record. And also older people, as they lose, the older you are losing your job, the less likely the chances of finding another job right away, simply because as you move up, a lot of companies, they call it age discrimination, and they try to avoid it, but it does happen. The older you are, the less likely a company is to hire you at an entry position, because if they have to train you, there's less chance that you're going to be there for a long period of time, and they don't want to invest that money into someone who's only going to be there for a few years before retirement. So that is probably what I would see as the biggest lurking variable there is employment status. That older age groups and people with arrest records are also more likely to be unemployed. So that might be the cause of their homelessness rather than their age or their police history. Other than that, I don't see anything else that could be a lurking variable for that. Unless I could maybe see, but they did test for mental illness. As you grow older, there's the higher chance of having any sort of like a seasonal affective disorder or depression, anxiety disorder. And of course, having a mental illness makes you more likely to have a police record in many cases. So that could possibly be a lurking variable, I guess. Otherwise, I don't really see anything else. Any other questions on the OCE for S3? Does the study provide evidence of a causal relationship? Okay. Causal means it's a cause and effect, causation. So does it say do the risk factors cause homelessness? And that answer Statistics never capable of showing a causal or a cause and effect relationship. All it can show is a correlation. It shows that people that have those factors are more likely to be homeless, more or less likely to be homeless. But the thing that causes those factors may also cause the homelessness. It isn't that the arrest record caused them to be homeless. It's that being unemployed caused them to do things to, it might even be that being homeless caused them to have the arrest record. They did things to try to secure food or whatever that caused them to be arrested. Any other questions? Okay, so now what we're going to be looking at today is new stuff. I want to talk just a little bit about something called the normal distribution. Because the normal distribution is really what all this stuff is dependent on. And a normal is a probability distribution, also kind of like a frequency distribution. We talked briefly about those dot plots, where we put dots above the number values on the plot. And we saw that as we put those dots above those values, that those dots ended up making a shape that was roughly a bell shape. And that's what the normal distribution is, that bell curve that you hear about so much. Well, the normal distribution, if this were a formal statistics class, and those of you that go on to the statistics class will see the probabilities here. The center of that bell curve, that normal distribution, is the center of the data. And that's usually either the mean or the median or the mode, depending on what we're using. For this class, we're going to be talking mostly about the mean. And then the width of it, the spread of it, is determined by standard deviations. If you go out one standard deviation, we don't know really, that term standard deviation is new to us right now. That's a way of describing how spread out the data is, and it's just a number you calculate. If you go out one standard deviation on each side of that mean, about 68% of the data falls in there. If you go out a second standard deviation, about 95% of the data falls in that range. That's what we're going to be concerned about right now, is that percentage, that 95%. And you can go in a little bit narrower, you get a little bit less, smaller than 95% and whatever. But that bell curve really is the heart of everything we do in statistics. So what we're going to be looking at today is we're going to be looking at estimating. We've talked a little bit a couple of weeks ago about populations, the population of interest and a sample, and the fact that we take that sample out of the population for many reasons, time, expense, ability to identify the population, all sorts of things. We have statistics and parameters. Statistics and parameters are very similar. Which one of those two describes the population, a statistic or a parameter? Do you remember? The parameter describes a population. The statistic is calculated from the sample. We take the sample and we can calculate the statistic. Well, if we know the population parameter, there usually is no reason to ever take a sample and find a statistic. The reason to take a statistic is an attempt to estimate that population parameter. Talking about the election, which is what the first example problem we're going to look at is going to be about. They did a lot of polls before the election. Usually between 500 and 1,000 people they called and polled, trying to predict who was going to win the election. What they were trying to estimate was the percentage of voters, the percentage of the voting population that was going to vote for one candidate or the other. So they took a sample because they couldn't call every voter in the United States. They really couldn't even identify who was going to vote. So they took a sample and they tried to use that sample information to estimate what the parameter was. So what I want you guys to do is in S4 here, problem situation 1, polls in the 2016 presidential election. There's information given there on a poll from that election. They're talking about statistics and parameters, and they're talking a little bit about margin of errors and confidence levels. I want you just to take about 3 minutes and read through that quick. It's about a page and a half long. I'll give you about 3 minutes to look through that. Then I want to discuss it, and we'll work through some of those questions together. Okay, so let's take a look at this situation. What they're saying is the poll, and we're not going to worry about the other candidates right now, showed Hillary Clinton getting 44% of the vote and Donald Trump getting 40% of the vote. But yet, after the election was over, Trump ended up winning. Why is that? Why could the poll show one candidate winning, but in reality, the other candidate won? Well, there's something called sampling error. Sometimes can be referred to as sampling bias. You took a sample, and we're assuming, or at least hoping, that's a representative sample. The items, the numbers we draw from that sample are the same as, or at least really close to, the numbers, the parameters of the population. In this case, those sample statistics, these are statistics because they're drawn from the sample, were not good estimates of the population parameters. Now, did anybody notice after that table was given, they mentioned something called a margin of error? What was the margin of error for this data? They said plus or minus 5.5 percentage points. Now, there's a difference between plus or minus 5.5% and plus or minus 5.5 percentage points. 5.5% would mean you'd have to find 5.5% of those numbers and add or subtract it. 5.5 percentage points is just 5.5 added on or subtracted from the percent. But then it also says something at 95% confident level. So that's an important statement that we'll talk about at some point. So for right now, the question is, question number 1 there, do you think the actual percentage of all likely general election voters in Pennsylvania who were planning to vote for Donald Trump a week before the elections was exactly 40%? So what they're asking is, was the Trump vote exactly 40% a week before the election? Do you think that is true? Yes or no? No. Why not? Yeah, chances of the poll, the survey, getting us exactly the correct answer for the whole population is pretty low. If the survey was done well, would you expect to be close to that? You would, yes. You know, this survey, how many people were surveyed in it? If I remember right, it was like 405 people. There are, I think, like 8 or 9 million people in Pennsylvania. You would assume that at least probably 2/3 to 3/4 of them are registered voters. So you're thinking about 5 million voters, 4.5 to 5 million voters at least. Only 405 people might be kind of a small sample. So then the question is, they stated this plus or minus 5.5 percentage points. What does that mean? Well, Clinton, it's acknowledging that they don't think that these numbers are exactly on. It's saying Clinton, we don't necessarily know that she's exactly 44%, but we'd expect it to be how close to 44%? 5.5 percentage points, yes. So what that's saying is they're saying 44%, but it could be 5.5% less, percentage points less, which would be 38.5%, all the way up to, yeah, come on, what do you need? Just start if they come in late, just write a start time on the top of their test. You bet. So then for the end, or for the higher value, there might be 44%. It could be 5.5 percentage points higher. So that would be up to 49.5%. So when they stated this in this survey, that the percentage of people that plan on voting for Clinton was 44%, but then listed that 5.5 percentage points margin of error, what they're really saying is chances are the percentage of people that will vote for Hillary Clinton are 38.5% to 49.5%. So what I want you to do right now is I want you to find that range for Trump. I'm going to give you just a few seconds to find that range for Trump so that we can compare them. So what do you get for a range for Trump? Perfect. Now, as we compare these numbers to Clinton, what do we notice about those ranges? Okay, very good. But probably a better way to display these would be a number line. Let's take a look at a number line here. I'm going to go, this is 35, 40, 45, and 50. So the number given in the original study for Clinton was 44 right here. The number given for Trump was 40 right there. Those are referred to as point estimates. Bless you. They give a single value, a single point. Now you look at those point estimates, it looks like Clinton's quite a bit higher than Trump. But now if we throw in that margin of error, Clinton went down as low as 38.5 right here, and as high, bless you again, of 49.5 all the way up to there. Trump went as low as 34.5, somewhere in here, but as high as 45.5. If we displayed them like that, yes, it looks like Hillary Clinton's slightly higher, but you can see they overlap quite a bit, don't they? In fact, there's more overlapping than there is not overlapping. From here to here is overlap, which would tell us that this is really too close to call. Yes. That's not quite a box and whisker plot yet. A box and whisker plot involves the mean or the median, and then quartiles and minimum and maximum. So that requires multiple data points. It's describing a set of data. Yeah. Yeah. Oh, when you go to print them off? Yeah, I can go back and reopen those for you again. On break here, I'll do that for you quick. Yes, yeah, definitely. We'll open those up for everybody just to make sure everybody has time. Sure, no problem. So what this is called here with those ranges given is an interval estimate. What determines the size of that range comes down to this number we had up here at a 95% confidence level. What does that mean? Well, that's kind of a tricky concept. And it goes back to this bell curve that we saw. If we looked at the population, on any given day, if we were able to actually gather information, if we were able to do a census on the whole population, on any given day, the numbers are going to change a little bit. But there's going to be a number that is the most common. That's going to be the highest point on our curve. And then there's going to be, as we move away from that most common point, it's going to be less and less common. So the curve goes down. Points that are further away, there may be days where people, a scandal comes out, so people are very opposed to one candidate or another. And the other ways, there may be something where a scandal comes out on the other candidate, so people become strongly in favor of that one. So as you look at all of these different values from day to day or hour to hour even, there is that center, like we said, in our bell curve. And then there's deviations, the changes. So as we move out from that center, there's a certain percentage of values that are going to fall within that range. And we want to go out a range that creates 95% of the values, that contains 95% of all of those different values gathered on different days. Well, when we took this survey, we don't know what that population mean is. This is from the population. We don't know what that center of that curve is. But we do know that 95% of the data, 95% of all the different results are going to be within 5.5 of that. So if we know that 95% fall within 5.5 of that, when we take a survey, and let's say we get a survey result, so down here are going to be the surveys, do you think we're going to get the same result to the survey every time? No, we're not, right? This is our population parameter, but we might take a survey one day and get a value that's much lower than the population parameter. The next day, something might change and we might get a value that's larger than the population parameter. Something else might happen the next day, we get something even way larger than the population parameter. And it keeps changing from day to day. But what we know is 95% of those should be within this range of the population number. So since that range is 5.5 on either side, if I take each of these sample amounts and I go 5.5 on either side, I create ranges that should most of the time contain the population parameter. Now notice I've already got one on here that does not contain it, and that's fine. It won't always contain it. The way it works, that 95% confidence, what that means is if I repeated this over and over and over again, 95% of these ranges would contain the true population parameter. Now we can see here we've got one that missed it. Well, we would expect 5% of those samples, if we made that range around the sample result, we would expect 5% to not quite contain that population parameter. So that's what 95% means. A lot of people think, well, it means there's a 95% chance that this range contains the population parameter. That's not quite right. It means that if we repeated this sampling process over and over again and created these, found the center and created these ranges, that 95% of the time those ranges will contain the true population mean. That's slightly different than saying it's a 95% probability or 95% chance. So that's the idea of a confidence interval. So the next one, they're asking, Trump eventually won Pennsylvania with 47.6% of the vote. Is that within the parameters of this survey? No, why not? Yeah, the range of the survey for Trump would have been 34.5 to 45.5. 47.6 is outside of that. So if we looked at the graph, 47.6 is somewhere out here. Well outside, it's over two percentage points outside of the range given for Trump with the margin of error. So that is not a good survey. So what that is saying here is this survey sample was not a representative sample. In other words, the results of the sample did not accurately reflect the population. Or did it? Because this sample was taken a week before the election. What are some things that could happen during that week that might change opinion? Could voter opinion have changed? Okay. So new information is one. And the second one's also a good one. They may have decided to vote or not to vote. There may have been people, when they surveyed them, they usually ask, are you likely to vote in the election next week? Some people said, no, I don't think I will vote. But then at the last minute, they decided, yeah, they wanted to. Or the other way around. They may have said, yeah, I'll vote, but then at the last minute, they didn't. If you recall in this last election, just a few days before election day was when a lot of the Russian leaky links information started being released that painted Miss Clinton in a very bad light. So that may have not only caused some people that were going to vote for her to stay home and not vote, it may have even caused some people that were independent or on the fence to decide to vote for Trump instead of her. The other thing, I don't know if they showed it in this one, if they gave, Gary Johnson was the third candidate listed. And they had Gary Johnson listed at 7%. But we now know that 7% meant anywhere from 1.5% to 12.5%. Well, Gary Johnson actually ended up with somewhere around, it was like 2.5 to 3% of the vote. Still within the range, that 5.5% margin of error, but it's on the very low end of that range. And one of the suspicions is many of those voters, when they were polled, it's easy to say, yep, I'm going to vote for Gary Johnson. I'm voting for the third party candidate. But when it gets right time for the election, maybe some of those people were voting for Gary Johnson because they wanted change. And when it came time to vote, they decided to vote for one of the other candidates because they knew Johnson couldn't win. And there was one of the other main candidates that they really didn't want to see win, so they voted against him. Some people may have voted for Trump because they didn't want Clinton to win. So even though they said they were going to vote for Johnson, they voted for Trump just to stop Clinton. A lot of things like that could have happened to adjust our data. Any other things you can see that might have made things change? Okay, it's 11:18. We're a couple minutes early, but let's go ahead and take our break right now. Okay, we've got everybody back in, so we just as well get started again, get her done with. Second part of the class here, we're going to actually do some number crunching. But we want to we're going to start out looking at margin of error and confidence interval. This is the little paragraph before number 5 in S4, question number 5. So we're going to just kind of read through that paragraph quick. Pew Research Center survey conducted June 7th through July 5th, 2016, questioned U.S. adults on their views about the 2016 presidential election. Among 4,602 respondents, and it breaks it down by web and by mail, the survey found 59% of U.S. adults experienced election fatigue. They felt worn out by the amount of election coverage in the news. The survey reported a margin of error of 2.3%, percentage points, at the 95% confidence level. If you haven't noticed it yet, 95% confidence level is the most common confidence level used. So what they're saying, first of all, we have 4,602 respondents. Of those, 4,172 were on the web, and 430 were by mail, regular mail. So from that situation, question 5 there wants you to identify two things. What is the sample size, which we just identified right over here, but it wants you to find the sample statistic. So what is the statistic given in this situation here? There's one of them given. Can anybody see what it is? Remember, a statistic that this is a number that describes the results of the sample. The survey found that 59% experienced election fatigue. Election fatigue is really just a fancy term for saying they're sick and tired of hearing about it. Now, if there were a population parameter, which is number 6, what would it be? What is the population of parameter of interest that we're trying to study here? Not a number, but just a description of it. There isn't a number given. It's what percentage of what is our population? That's the sample size. And what was the quality of those people that got them into the sample? Well, they volunteered, but they were sampled because they were voters. So the population is all voters, all people who voted in the election. What percentage of voters experience? What did they ask those people surveyed about? Election fatigue. Very good. So the population is all the voters. And so the population parameter that we are interested in here, the question we're trying to answer is what percentage of voters experience election fatigue? So the next question is, before we go on to number 7, do you think this sample is a good sample or is it biased in some way? I'm going to have you focus just on these two things here. Almost 4,200 were web submissions and only 430 were mail submissions. What is that? Go ahead. What does that possibly tell us about our voters? Okay. Yeah, if you look at that, only 10% were mail submissions, 90% were submitted by web. Well, there's probably way more than 10% of voters that don't have internet. So the larger proportion were from people that had internet access. If they have internet access, what does that tell you possibly about the information they're getting? Okay, very good. Access to web information. Because they're submitting on the web, they have access to web information. And as that Sam said, it might be biased to a candidate. In other words, they might be more likely to be tearing apart another candidate, criticizing a candidate, or being negative type advertisements. At the very least, having access to web information, this person is just plain going to have more information in front of them. I mean, even now, every time I go online, I still see pop-ups that want to talk about politics and the results of the election. Back last October and November, those pop-ups were all over the place in your news feeds and stuff. If you were on Facebook, it was on the side of the page everywhere. So, you know, if they have the fact that they submitted them through the web and have web access means there's a good chance that they were just plain seeing more information than the people that didn't have web access. And if they were seeing more information, it's probably more likely that they experienced fatigue because they saw more of it. So then they give a margin of error of 2.3 percentage points. So what would really be the interval estimate of this sample? The point estimate, of course, is what? The point estimate was that number given of the 59%. That is the point estimate. The interval estimate then is using that 2.3%, plus or minus 2.3 percentage points. So what would the low end of that be? $59 minus 2.3. Perfect. 56.7% to 59 plus the 2.3, which would be 61.3%. So according to this information, if this survey is accurate, we can say that 95% confidence that between 56.7 and 61.3% of the voters are fatigued or tired of hearing about the election. So I'm going to make this claim. Over half of voters are fatigued. Does this result support that claim? Yeah, it does. What if it gave the result of 54% plus or minus 6%? What range would that give us? What is that interval? What interval would that be? Perfect. Perfect. If that were the interval estimate, would that support the claim that over half of the voters are fatigued? No. Can you tell me why not? Perfect. 48, that range, that interval is saying it could be as low as 48%, which is less than 50. Even though most of the range, if I'm looking at a number line here, 45, 50, 55, 60%, this interval goes from 48 on up to 60. Even though most of the range is above 50%, some of it is below 50%. So it's possible to be below 50%. So this would not support the claim that more than half of the voters are fatigued. This one up here, however, everything is above. It goes from 56.7 up to 61, with 59 being the center. That definitely supports it, because the whole interval is above the 50% range. So that's one of the things when we look at statistical processes and statistical decision making, even though this one here gave us a number of 54%, since that interval, once we put the margin of error on it, still goes down below 50%, it's not supporting that it's greater than 50%, even though the 54 is larger than 50. Because the interval dips below 50, we can't use that as evidence that that rate is more than half, more than 50%. Okay, so now what we're going to look at problem situation 2, which is legalizing marijuana. What's that? Go ahead. The confidence level, what that's saying is because it's 95%, what that is saying is 95% of similar samples taken, if we constructed this interval, would contain the population parameter, the true population parameter. So what we're going to do right now is we're going to use Excel, and I will do the Excel work for us so that you guys don't have to worry about it. If you want to follow along doing it, that is wonderful. I'm going to make a list. You can see here in problem situation 2, what they're doing is they've done a survey of 100 residents. Actually, it's not even a survey. This is a census. Does anybody remember the difference between a survey and a census? Exactly. In a census, yeah. In a census, we've gathered information from everybody in the population. So in this situation, we've made up an imaginary city that has 100 people in it. So, and then we were able to survey all 100 people. We were able to somehow get them to respond to that survey. But it's not even a survey, again, it's a census. So we got them to respond to that census and give us results. And so what's listed there on this page for problem situation 2, you can see it's 1 through 100 with a Y or an N next to it. Y indicates that they are in favor of legalizing marijuana, and indicates they are not in favor. So I'm just labeling, we've got that sheet in front of us, I'm just labeling them 1 through 100 here. And we need to randomly select. We're going to randomly select 15. So that's why I have my page set up so that I can still see the top 15 numbers. What I'm going to do is this. I'm going to put in a random number generator here. I'm just going to put equals RAND equals rand, generates a random number. Oops, I've got to put parentheses after it if I remember right. There we go. What you got to enter is equals RAND, and then you got to put open and close parentheses after it. And I'm just going to fill this down for all 100 values. And you can see it creates a random value for each of them. Now you got to be careful here. Watch that top number closely. If I do something here, notice those numbers all changed. That's because the random number generator is a calculation to Excel. So anytime I do things that would cause Excel to recalculate, it recalculates the random numbers as well and assigns a new random number, which is actually going to be good for our purposes here in the next 45 minutes or so. So what I'm going to do is I'm going to highlight these 2 columns and I'm going to sort. I'm going to go to Data, and I'm going to select Sort. And because I have 2 columns here, I have to tell Excel which column to sort by. I'm going to say we're going to sort by column B, and we're going to go smallest to largest. So what that means, you could go largest to smallest, it would work just as well. But what I am doing is I am selecting the 15, the ones that got the smallest random value assigned to them are going to be the ones that I select for my sample. So I clicked OK, and I get, here are my top 15 values right here. So those are the ones that I am selecting for my sample. So what I want to do here quick is if I look number 77, are they a yes or a no? 77's a no, aren't they? 21, yes or no? Yes. 31. No. 74. Yes. 37. Yes. 56. Yes. 82. 98. Yes. 45. Yes. 47. No. 69. Yes. 36. No. 13. No. 81. No. And finally 52. Yes. Okay, so now I'm going to create a little table over here. This is my first. Now notice every time I hit enter, those numbers there are changing. That's because, again, it recalculates those random numbers. But we had already sorted them, so those top 15 are our, they are the ones that we wanted in our sample. So how many yeses do we have here? Yep, count them out, please. I'm getting 9. So I got 9 out of 15. Well, if I divide 9 by 15 here, I'm going to get 0.6. If I looked at all 100 there, we can see on top it tells us the population proportion is 0.6. So this sample that we took happened to give us exactly the same result as the whole population did. So here's a case where our sample statistic of 0.6 is exactly equal to the population proportion. Couldn't have planned that one out, huh? So I'm going to erase those results quick, and I'm going to resort these. What I'm doing is I'm taking a new sample. If I take a new sample, do you think I'm going to get the same result? Probably not. Do you think I'm going to be close? Yeah, possibly. Okay, well, let's do that. We've got 66 there. What's that response? No or yes? No. 31? No. 50? Fifty is a yes. 90? Yes. 76? No. 52? 73? Yes. 43? No. 13? No. 91? Yes. 64? Yes. 5? Yes. 99? No. 37? Yes. And 100 is yes. So let's count those up. 1, 2, 3, 4, 5, 6, 7, 8. We got 9 again, didn't we? Well, let's try it again. Let's sort it again. We're going to empty these out. So we got a new sample. So what's the response for number 75? Yes, 64. Yes, 71. No, 86. Yes, 60. No, 45. Yes, 78. Yes, 4. Yes, 58. 58, yep. Yes, 9. No, 18. No, 12. Yes, 35. Yes, 47. No, and finally 16. No, let's count them up again. 1, 2, 3, 4, 5, 6, 7, 8. Oh boy, that's discouraging. I got 9 again, so we got 0.6. So these are coming up to be really close to 0.6. The point of this is you're supposed to see them coming out a little bit different. Let's try it again. Okay, so we sorted again. So we're going to do those top 15 again. 98. Yes, 36. No, 21. Yes, 45. Yes, 66. No, 79. Yes, 81. No, 95. Yes, 57. Yes, 69. Yes, 99. No, 89. No, 19. No, 64. Yes, and 68 is a yes. How many people want to bet we're going to get 9 again? 1, 2, 3, 4, 5, 6, 7, 8, 9 again. Wow. It's not supposed to be getting the same, no. There's some random chance going on here that's really 4 times in a row is a little weird, yeah. That might be my signal to buy a lottery ticket today. So I sorted them again. Let's look now. Let's do 28 is, yes, 4. Yes, 64. 55. Yes, 27. Yes, 17. Yes, 54. Yes, 8, or 62, I should say. No, 73. Yes, 2. Yes, 76. No, 31. No, 72. Yes, 18. No, and 22. Okay, let's see what this gives us when we count them up. 1, 2, 3, I get 10. Finally, we got a difference. Woohoo! That came up again. By the way, the first 7 here were yeses. The chances of getting 7 yeses in a row. Now the chances of getting yes are 0.6 because there's 60 out of the 100 are yeses. But 7 in a row would be 0.6 to the power of 7. That's less than a 3% chance of getting 7 in a row. That's one of the things about statistics is just because it's unlikely does not mean it's impossible. Okay, let's do this again. So let's go through 27. Yes, 21. Yes, 28. Yes, 72. Yes, 97. No, 69. Yes, 30. 44. No, 75. 17. 22. 78. 11. 87. And 94. No. So let's count these up here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we're different again. Let's do one more and then we'll plot these and we'll see what it looks like. So we'll sort this again. Now this exercise works a lot better if you have a bigger class. You can divide the class up into about 5 groups and have each group do this, 7 or 8 times. And then you can bring them all together. Well, let's do this one more sample here. Number 55 is 21, 97, 29, 61, 58, 92, 31, 68, 38, 32, 50, 54, 18, and 94. 94 is no. Yes, I got the wrong thing there. So let's count these up. 1, 2, 3, 4, 5, 6, 7, 8, 9 again. We're back to 9. I'm going to put in an 8th one here just to balance out the data a little bit. Eventually, we would have got one that was less. But what I'm going to do here is I am going to now graph these sample proportions, but I'm going to do it this way. I got answers of 0.6. Sorry, let's go back up. Thanks, guys. I got answers of 0.5333, 0.6. How did they do? What's the highest 3? 54. That's usually how they did. That's not too bad. That's why I was disappointed the last couple of years. Nobody got over like a 60% ever on this. So we got 0.7333. So we had the 0.533 was once, the 0.6 was 5 times, and then once for each of the others. If I graph this using a dot plot here, or actually just a simple line graph probably, I'm going to do this format data series. Let's do a select data. That's what I want. Series 1 is going to be shut off. Okay. There we go. Select data. I need to turn off series 1. And we're going to do, crap, I did it again. There we go. I got to get to where I can actually see the data. There's what I wanted. So this gives us, this blue line here gives us our data. What we see is, that's not working worth a crap, is it? Okay, anyway, let's do it by hand. What we end up getting, technology is failing me right now. So anyway, what we have here is a 0.533, 0.6, 0.667, and the 0.733. We had one for the 0.533. We had 1, 2, 3, 4, 5 of the 0.6, one of the 0.67, and one of the 0.733. If we had kept doing this, we would have ended up getting points similar to this, and it would have looked more like that bell curve like that. We just don't have time to keep going. We really, the magic number is 30. Really having 30 of these samples, we should get a shape that looks like that bell curve. We just didn't have time to do 30 samples. You can see taking 7 samples took quite a bit of time, and I don't want to keep going. But the question I want to pose to you is, if I change this, instead of taking a sample of 15, and instead I took a sample of only, let's make that go away, there we go, of only 10, do you think that would give us similar results? So let's take a look at this. This was for the sample size of 15. I'm just going to put n equals 15 as the notation for that. Down here, I'm going to do the sample size n equals 10. So now I'm only going to look at these first 10 numbers for my sample and see what happens. So let's go ahead and resort and take another sample here. Again, we're only going to look at the top 10. So what's the result for number 83 was, 83 is yes, 94 is no, 62, no, 82, 46, 89, no, 43, no, 25, 66, no, and 80. So for our first sample here, we have a result of, what is it, 1, 2, 3, we only have 4 out of the 10, so that's 0.4. Let's do a second sample. So 57. Yes, 95. Yes, 6. Nope, 21. Yes, 46. Yes, 25. No, 37. Yes, 90. Yes, 15. And 91. There we actually had 8 out of the 10. So that's 0.8 is that proportion. Now you can see when we did the sample size of 15, we didn't ever have anything as small as 0.4 or as large as 0.8. So by taking a smaller sample, what do you think that does to these sample results? Do you think that makes that interval estimate smaller or larger? The margin of error, let's do it this way. Do you think the margin of error would have to be bigger if we did a smaller sample size? Or do you think the margin of error would be smaller? It's a tough question, isn't it? Well, I'm going to flip back here to the Word document for a second. When we do this, when we had n equals 15 for a sample size of 15, our points were relatively close together. But we saw when we did the sample size of 10, we were getting results that were scattered all over the place, weren't we? Which curve is more spread out? N equals 10 is way more spread out. So if you think about it, if we want to contain 95% of that data, remember that margin of error is saying we want to go from the center out far enough that we contain 95% of the data. Which one's going to have to go out further to get 95% of it? The n equals 10. So the point that we kind of wanted to show here with this second part is the smaller the sample, the larger the margin of error. Larger the sample, the smaller that margin of error is going to be. Now, what if we don't need to be so sure? This is, of course, 95% confidence level. What if I want to reduce the confidence level? Let's say I only want to do a 90% confidence level. What that means is I only want to go out far enough to contain 90% of the data. Is that interval going to be larger or smaller than the 95%? It's kind of a weird wording on the question, isn't it? If I had to go out this far to contain 95% of the data, let's say I change my mind and I only want to contain 90% of it. Would it make sense? Do I go all the way out here to the outside of that, or would I stay on the inside? Well, 90% is smaller than 95%, isn't it? So that would stay on the inside. So if I want to talk about confidence level of confidence, whatever, if I want to increase the confidence level, it results in an increase in margin of error. If I want to increase the sample size, we saw that making the sample size larger, up here, the larger sample size had a much smaller margin of error. It decreases the margin of error. So as we go through, when you're dealing with analyzing data and statistics, there's a balance between level of confidence and sample size. If we want to be more confident about our data, more likely to be within a certain range, then we have to take a larger sample. But taking a larger sample takes more time and usually more expense. So if we have a budget, we've got to learn how to balance that sample size with the confidence level. That all depends. The desired confidence level depends on the desired margin of error. Really, what we're talking about is getting within a desired margin of error. That desired margin of error depends on how critical it is that we be accurate. If we're trying to predict who's going to win the presidential election, nobody's going to die if we're wrong. So it's okay to take a lower level of confidence. If we are testing an airplane to see if it meets specs, well, there it's pretty serious that we don't make a mistake. So we would want to test with a larger confidence level. The standard, of course, as we said, is usually that 95% level of confidence. Okay, that's wrapping up everything we had for today. So for next week, I would like you to work on out-of-class exercises here for S4, and then the P&L for S5. Those, again, I'd like to have you have them done for next class on Monday. Those will be due on Tuesday of next week. And then don't forget we have stuff that is due tomorrow, the OCE for S3 and P&L for S4, which are set to be due tomorrow, Thursday. We only have 3 more lessons left to go. And then we have a day of review, and then we have the final exam. What I think I'm going to do is, since that final exam is on Canvas, I am going to open it up so it's open up probably like noon or so on Tuesday. Do you guys have any work schedules or anything that keep you, is afternoon, morning, or anything like that better for taking a test? From Tuesday until Wednesday. It would be open during this time too, but I'll probably have it so it's at night. Okay, so what I'll do is I'll probably open it up so you can take it anytime from about 10:30 in the morning on Tuesday until the end of this class on Wednesday. Yep, it's in the Canvas thing. Is there anybody that really, really strongly prefers to have it done on paper? I mean, I can turn it into a printed version if you'd want me to. Okay. I will turn it into a paper copy for you, and I will send it out. I'll have it just sent to the campuses, so you guys can either come in and do it on paper, or you can do it on Canvas. But if you do it on paper, we'll have it done in class then on that Wednesday, was it the 20th? Yeah, it'd be Wednesday the 20th. We'll have it available in class if you want to do it on paper. Yes, I'll make sure I get it translated into paper for you. Any other questions? Any questions? Okay, well, you guys have a great weekend, and we'll see you next Monday.